Hello everybody, and welcome to the second talk on new perspectives in Hermitian K-theory, given as part of the virtual seminar, New Perspectives on K and L Theory. Let me start with a bit of recollections from the previous talk. Recall that a Hermitian infinity category is a stable infinity category C equipped with a Hermitian structure, which, by definition, means a quadratic functor kappa from C up to spectra. A Hermitian functor f eta from a Hermitian infinity category C kappa to a Hermitian infinity category C prime kappa prime consists of an exact functor f from C to C prime and the natural transformation eta from kappa to the restriction along f of kappa prime. We say that C kappa is Poincaré if there exists an equivalence of infinity categories D from C up to C, together with a natural equivalence of functors in two variables x and y between the bilinear part B kappa of kappa and the mapping spectrum in C from x to dy. In this case, D is essentially uniquely determined by kappa and is called the associated duality. Any Hermitian functor f eta between Poincaré infinity categories C kappa and C prime kappa prime determines a natural transformation tau eta from f d kappa to d kappa prime f up. We say that f eta is a Poincaré functor if tau eta is an equivalence. This can also be formulated by saying that a Hermitian functor between Poincaré infinity categories is Poincaré if it is compatible with the dualities on both sides. The collection of Poincaré infinity categories and Poincaré functors between them can be organized into an infinity category, cat P. This infinity category has many favorable properties. For example, it can be shown that cat P admits all small limits and colimits, and that the forgetful functor from Poincaré infinity categories to stable infinity categories and exact functors between them preserves all small limits and colimits. Another favorable property of cat P is that it is semi-additive. It has a zero object, which consists simply of the zero stable infinity category and the zero quadratic functor on it, and products and coproducts in cat P coincide. This means that every product-preserving functor from cat P to some other infinity category with products canonically lifts to a functor taking values in infinity monoids in E. We then say that a product-preserving functor f from cat P to E is group-like if its refinement to infinity monoids take values in group-like monoid objects. Here we recall that a monoid object x is called group-like if its shear map from x times x to x times x is an equivalence. This is the map whose first component is given by the projection on the first component here, and the second component is given by the sum, the monoid operation on the two components here. Any loops on a monoid object is automatically group-like. A consequence of this is that the functor that takes a Poincaré infinity category to its Grothendieck-Witt space is group-like, since it is defined as the loop on another product-preserving functor. A non-example of a group-like functor is Pn, the functor that sends a Poincaré infinity category to its space of Poincaré objects. It is product-preserving, but not group-like. Our next goal is to study the additivity property for the Grothendieck-Witt space. This is an analog in the Hermitian setting of the classical additivity property of K-theory proven by Waldhausen. In order to formulate it in our present setting, we will need a few definitions. We start with the following. So, a sequence of Poincaré functors from C kappa to d phi to ipsi with vanishing composite is called a Poincaré-Verdier sequence if it is both a fibre and a cofibre sequence in cat P. We say that this sequence is split if P admits both the left and the right adjoint. Poincaré functors that can be found on the left in Poincaré-Verdier sequences are called Poincaré-Verdier inclusions. Similarly, they are called split Poincaré-Verdier inclusions if they are found on the left in split Poincaré-Verdier sequences. In a similar manner, functors that appear on the right in Poincaré-Verdier sequences are called Poincaré-Verdier projections or split Poincaré-Verdier projections if they occur in a split Poincaré-Verdier sequence. These two properties of functors also admit an explicit characterization. So a functor f eta from C copa to d phi is a split Poincaré-Verdier inclusion if and only if f is fully faithful, admits a right adjoint, and the natural transformation eta is an equivalence. In a somewhat dual manner, a functor p theta from d phi to ipsi is a split Poincaré-Verdier projection if and only if p admits a fully faithful left adjoint g, and the map that we obtain from the restriction of psi along g to phi is an equivalence. Let me start with an example of a split Poincaré-Verdier sequence that in our context is can say the most important example of such a sequence, and is also the universal example in a suitable sense. So in order to define it, we first consider the following definition. So for a Poincaré infinity category C copa, we define met C copa to be the Hermitian infinity category whose objects are arrows L goes to X in C, and whose Hermitian structure is given by the functor that sends the arrow L to X to the fibre of the corresponding map from copa X to copa L. One can then show that met C copa is Poincaré with duality sending the arrow L to X to the arrow from the fibre of the map from dx to dl to dx. A Hermitian object in met C copa then corresponds to a Hermitian object xq, a map from L to X, and a null homotopy eta of the restriction of Q to L. Such a Hermitian object is Poincaré if and only if xq is Poincaré and eta exhibits L as a Lagrangian in X. We call met C copa the metabolic Poincaré infinity category of C copa. Its Poincaré objects correspond to metabolic Poincaré objects in C copa, or more precisely, metabolic Poincaré objects in C copa equipped with a prescribed Lagrangian. We then have the fundamental example of a split Poincaré-Verdier sequence, the metabolic sequence. It is a sequence involving a Poincaré infinity category, its shift, and the metabolic Poincaré infinity category in the middle. So from met C copa, we have a Poincaré functor to C copa, which sends the arrow L to X simply to X. The fibre of this functor consists of the full subcategory of met C copa spanned by the arrows from L to 0, or from L to a 0 object. The underlying infinity category of this fibre is clearly just equivalent to C itself. And if we look at what will the Poincaré structure of met, what does it give to an arrow of the form L goes to 0? It gives the fibre, so in this case, copa of 0 is 0, and it gives the fibre of the 0 map from 0 to copa of L. This is the same as the loop on copa of L, and hence we obtain here a copy of the shifted Poincaré infinity category. One can then show that this is indeed a split Poincaré-Verdier sequence using the explicit criteria from the previous slide. Now, when we will define the notion of additivity, it will be convenient to have something slightly more general than a Poincaré-Verdier sequence or a split Poincaré-Verdier sequence, and to instead work with squares. Now, a commutative square of Poincaré infinity categories, as appearing here, is called a Poincaré-Verdier square if it is Cartesian, i.e. a pullback square in cat P, and its vertical legs are Poincaré-Verdier projections. If these vertical legs are also split Poincaré-Verdier projections, then we say that this Cartesian square is a split Poincaré-Verdier square. Now, we now define for a functor from cat P to an infinity category E with finite limits, we say that f is Verdier localizing if it preserves final objects and in addition sends Poincaré-Verdier squares to fibre squares. Similarly, we say that it is additive if it preserves final objects and sends split Poincaré-Verdier squares to fibre squares. An example is that the functor Pn, which sends a Poincaré infinity category C copa to its space of Poincaré objects, is Verdier localizing. This is because it in fact preserves all limits. It is as it is a representable functor. It is represented by the universal Poincaré infinity category mentioned in the previous talk. I should also say that the property of additivity should be considered as the analog in the present context of Waldhausen's additivity, while Verdier localizing is analogous to Quillen localization property. Let us now consider some more examples. Consider the following diamond diagram. So here in the middle we have the Poincaré infinity category Q1. Recall that the objects of Q1 are spans in C, and the Hermitian form on such a span consists of choosing Hermitian forms compatibly on the three objects. And such a Hermitian form is Poincaré if and only if it exhibits the span as a cobordism. The functor D1 from Q1CQ to Q1C copa to C copa is called D1 from the as it appears in the simplicial object that we have in the Q construction, is the functor that sends a span from X to X prime via W simply to X. The fibre of this functor consists of those spans which start from 0. So they only involve the middle object W and the target object X prime, and hence the underlying stable infinity category of this is the infinity category of arrows, as in MET. And if one compares what will the quadratic functor of Q1C copa give on a cobordism starting from 0, one will obtain exactly the definition of the quadratic functor of MET. So the fibre of this face map is exactly MET. On the other hand, this functor, the vertical functor here, is defined as follows. It sends a span like this from X to X prime via W with maps alpha and beta to the pair fibre of alpha and dual of cofibre of beta. This is at least the definition on the underlying stable infinity categories, and this can be made into a Poincaré functor. And now one can verify that both this horizontal sequence and this vertical sequence are both split Poincaré-Verdier sequences. This means in particular that if we take any additive functor, then this functor will send the horizontal sequence to a fiber sequence and the vertical sequence to a fiber sequence. But one can even say a little bit more when F is group-like. This is because this is not a completely general split Poincaré-Verdier sequence, since this Poincaré functor D1 admits a one-sided inverse given by this functor F, which includes the fiber of this functor that we described here. So if you just simply observe what is the functor, what is the fiber of this functor, so it would consist of spans such that the fiber of alpha is 0 and the cofiber of beta is 0. These are simply the constant spans, and the category of constant spans is clearly equivalent to C itself. Also, if one compares the quadratic functors, one simply obtains a copy of C copa, and this C copa is exactly embedded via the degeneracy map that appears in the simplicial object of the Q construction. So this D1 has S, this face map has the degeneracy map as a one-sided inverse. And this means that if we have a functor F which is not only additive but also group-like, then it's not only that it will send the horizontal sequence to a fiber sequence, the value that it will give on the middle object will split as a product of the value that it gives on C copa and the value that it gives on MET. This is D-splitting. On the other hand, if you consider the vertical sequence, here the inclusion admits a one-sided inverse given by D1, and hence again we will have the similar type of splitting in the group-like case. And if one analyzes this situation sufficiently, one observes that it's not just that this product will be equivalent to this product, it is in fact via direct equivalence between the value of F on MET and the value of F on the hyperbolic category. So one can conclude from this diamond diagram that if F from cat P to E is a group-like additive functor, then in particular F will give the same value on the metabolic Poincaré infinity category and the hyperbolic one. More precisely, this equivalence will be given by this particular Poincaré functor obtained by this composition. Our next goal is to prove that the functor that associates to a Poincaré infinity category C copa its Grothendieck-Witt space is additive. A similar statement in the setting of exact categories with duality was proven by Schlichting. Our approach is a bit different and is based on the formation of cobordism infinity categories. And what we prove is in fact a statement already on the level of the cobordism categories, a statement of the following kind, which we call the fibration theorem. And it says the following. If we have a Poincaré functor from d phi to ipsi, which is a split Poincaré-Verdier projection, then the induced functor on cobordism infinity categories is a bicartesian fibration. Well, here a bicartesian fibration means a map that is both a Cartesian fibration and a co-Cartesian fibration. And what this means is that for any cobordism at the bottom, any cobordism in E induces not just a functor in one direction from the fiber over xq to the fiber over x prime q prime, and not only a functor in the other direction, but in fact an adjunction between the fiber of this functor over xq to the fiber over x prime q prime. Now, adjunctions between infinity categories always induce a homotopy equivalence on the level of realizations. This means that the family of geometric realizations of the fibers of P star is constant up to homotopy over the cobordism category of E. And from this, one can deduce that these are also the homotopy fibers of the induced map on geometric realizations. And a corollary of this is that the functors which send C copa to the geometric realization of its cobordism category and C copa to its Grothendieck-Witt space, which is just the loop on this, are both additive. Now, let us now indicate a little bit how we prove the fibration theorem. So I will describe here just one step in the proof, and this is the step of how to construct co-Cartesian lifts to cobordisms in E. So for this, we note that the fibration theorem has a non-Hermitian precursor, which was proven by Bauerich, who proved that if P from D to E is an exact functor which admits fully faithful left and right adjoints, then the induced functor on span infinity categories is a bicartesian fibration. In fact, in this case, already P itself is a bicartesian fibration. In addition, the co-Cartesian edges in the span infinity category can be characterized in terms of the Cartesian and co-Cartesian edges in D in the following manner. So a span in D is P star co-Cartesian if and only if alpha is P Cartesian and beta is P co-Cartesian. Dually, such a span will be Cartesian if now alpha is co-Cartesian and beta is Cartesian. And the following lemma will allow us to refine co-Cartesian lifts constructed on the level of spans to co-Cartesian lifts on the level of cobordisms. And the lemma says the following. So suppose that P theta is a split Poincaré-Verdier projection from D phi to ipsi. And suppose that beta from W to Y is a P co-Cartesian edge in D. Then the induced map on spectra from phi Y to the fiber product of phi W and psi Py over psi Pw is an equivalence. Let us indicate the proof of this lemma. So, since we assume that P theta is a split Poincaré-Verdier projection, in particular, we know that P has a fully faithful left adjoint G. In this case, we can characterize the P co-Cartesian edges in D in the following explicit manner. So, an error beta is P co-Cartesian if and only if the commutative square that we construct using the co-units of the adjunction between G and P is exact. Now, since again P theta is a split Poincaré-Verdier projection, we have an identification of the quadratic functor psi with the restriction of phi along G. It will hence suffice to show that phi sends this exact square to an exact square of spectra. Now, this is not automatic since phi is not an exact functor. However, it is not that far from being exact. It is only quadratic. For a quadratic functor, the obstruction to sending an exact square to an exact square of spectra can be measured by applying the bilinear part of the quadratic functor to the cofibers of the vertical and horizontal maps. Note here that since this is an exact square, the two horizontal arrows have the same cofiber and the two vertical arrows have the same cofiber. The value of the bilinear part on these two cofibers is what gives the obstruction to phi sending this exact square to an exact square of spectra. Now, since d phi is Poincaré, this bilinear part can be expressed in terms of the duality of D. It can be expressed as the mapping spectrum in D from this cofiber to the dual of this cofiber. We now use the adjunction between G and P in order to remove G from here and put it here. Now, when we move G to the other side and replace it with P, it can be also pushed forward against the duality because P is a Poincaré functor, so it commutes with the duality. So we can push it all the way to the cofiber, and we obtain that this mapping spectrum is the same as the mapping spectrum in E between the cofiber of P of beta to the dual of the cofiber of P of the counit. Now, since the adjunction between P and G is such that G is fully faithful, in this situation it follows from completely formal reasons that P sends the counit of this adjunction to an equivalence in E. So P of the counit is an equivalence, its cofiber is hence 0, and so this entire term vanishes. Since this was the obstruction for phi to send this square to an exact square, we deduce that phi indeed sends this square to an exact square. Now, how can we use this lemma? This lemma fits exactly when we need to construct co-Cartesian lifts to cobordisms. So what is the scenario when constructing co-Cartesian lifts? We start with a Poincaré object in D, and we start with a cobordism starting from the image of this Poincaré object in E. So we have a cobordism from Px, Pq to some yr via some w eta. So here eta is the homotopy between the restriction of these two forms to w. And we want to construct a co-Cartesian lift of this cobordism in cob D. Now, using that P from D to E is itself a bicartesian fibration, we can find a p-Cartesian lift alpha prime to alpha, so this would be some error from w prime to x. And then a pico-Cartesian lift beta starting from w prime and lifting beta so that it ends with some y prime living above y. We hence obtain a span lifting the underlying span of this cobordism. Now we want to endow this span, we want to make it into a cobordism. So this means that we need to put a Poincaré form on this span. Let us start by putting a Hermitian form on this span. So first, we have already a Hermitian form, even a Poincaré form, Q on X. We can always restrict it to a Hermitian form on W. In order to make this also a Hermitian form on the entire span, we now need to push this Hermitian form forward to Y prime. Normally, we can't do this. This goes against the direction of the variance of our quadratic functors. However, what the lemma that we had here exactly tells us is that this map is an equivalent. So this means that to construct a Hermitian form here on the domain, on the target of a co-Cartesian edge is the same as having the form on its domain and then extending it to the target downstairs in E. And what this means is that if you consider the space of ways to push this Hermitian form that we restricted from X to W prime to Y prime, to push it forward to Y prime in a way that is compatible with the R that we have downstairs, then this space is contractible. So we can essentially choose in an essentially unique manner a Hermitian form on this span. We now want to prove that this Hermitian form that we chosen, we didn't have a lot of choice, but we chose one, that this Hermitian form is Poincaré. And this follows from the following observation. One can prove that the duality on Q1 d phi preserves the full subcategory consisting of the spans which are co-Cartesian with respect to the map on the induced functor on spans. And the unimodularity or the Poincaréness of this Hermitian form can then be deduced by the unicity of Cartesian and co-Cartesian lifts. So what will end up happening here is that this Hermitian form determines some map this lift that we constructed to its dual. But from this observation, both this span and its dual are both co-Cartesian lifts of the span that we had downstairs. And the map that we constructed will be an equivalence or the identity downstairs. And hence, from the unicity of co-Cartesian lifts, this map induced by this Hermitian form will have no choice but to be an equivalence. And so we will deduce that this Hermitian form that we had no choice but choosing is in fact Poincaré. And this is the way that we construct co-Cartesian lifts to cobordisms. This is only one step of the proof to construct these candidates for co-Cartesian lifts. The rest of the proof is to actually prove that these lifts constructed in this manner indeed give co-Cartesian arrows. And the same for the dual construction involving Cartesian arrows. So let me not describe that part. So a summary of what we had so far. So having proven the fibration theorem, we know that the functor that sends a Poincaré infinity category to its cobordism infinity category sends split Poincaré-Verdier sequences to bicartesian fibrations. From this, one can deduce that the functor that sends a Poincaré infinity category to the geometric realization of its cobordism category is additive. And from this, one can deduce that the functor that sends a Poincaré infinity category to its GW space is additive. And I recall that this functor is just the loop on this functor. And let's see what we can deduce from this. So one corollary, we saw that we already know that GW is group-like, so now we know that it's group-like and additive. And we saw that any group-like additive functor gives the same values on the metabolic Poincaré infinity category associated to C copa and the hyperbolic Poincaré infinity category associated to C. Now we saw already in the previous talk that the Grothendieck-Witt space of the hyperbolic Poincaré infinity category is the same as the K-theory space of C. And so we deduce that the GW space of both met C copa and hype C is the K-theory space of C. Another thing that we saw for every group-like additive functor is that the value on Q1 breaks as the value on C copa and on the hyperbolic category. And so we can deduce that the Grothendieck-Witt space of Q1 C copa breaks as a product of GW of C copa and the K-theory of C. Now, if we apply additivity in the case of the metabolic sequence, we obtain a fiber sequence involving GW of the shifted Poincaré infinity category, GW of Poincaré infinity category, and in the middle, GW of the metabolic infinity category, all associated to C copa. Now, from this, we know that GW of the metabolic infinity category is the same as the K-theory space of C. And so this sequence actually becomes a sequence involving the Grothendieck-Witt space of C copa, the Grothendieck-Witt space of C with shifted copa, and in the middle, the K-theory space of C, where here this map just becomes the forgetful map from the Grothendieck-Witt of shifted C copa to K-theory of C, and here the hyperbolic map from K-theory of C to the Grothendieck-Witt space of C copa. And this is called the Bode-Genauer sequence. More precisely, this is the space-level version of the Bode-Genauer sequence. We are going to have later a spectral version of the Bode-Genauer sequence when we will define the Grothendieck-Witt spectrum. Now let's see what consequences we can get out of the space-level Bode-Genauer sequence. So for a Poincaré infinity category C copa, one can define the following spaces which measure the difference between K-theory of C and Grothendieck-Witt space of C copa. One space is the fiber of the hyperbolic map. This is often called the U space. And the second is the fiber of the forgetful map from GW to K. In a setting of forms over rings, these homotopy fibers measuring the gap between Grothendieck-Witt and algebraic K-theory were defined and studied by Karoubi, who proved in this context his fundamental theorem in Hermitian K-theory. Using the Bode-Genauer sequence, we can obtain a version of Karoubi's fundamental theorem for Grothendieck-Witt spaces in the setting of Poincaré infinity categories. And the theorem says that there is a natural equivalence between the V-theory of C copa and the loop of the U theory of C copa twice shifted. And the proof of this is direct from the Bode-Genau sequence, since both these things identify with the loop of the Grothendieck-Witt space of C shifted one time. As we can see, so for example, if we look at the U theory, so this is the fiber of the hyperbolic map. By the Bode-Genau sequence, the fiber of the hyperbolic map is the GW space of the shifted structure. So loop of U with the Poincaré structure twice shifted will be loop of GW with the Poincaré structure once shifted. And a very similar argument shows that the V space of C-COPA identifies with the exact same term. So this is the Karoubi fundamental theorem for Grothendieck-Witt spaces. And what can we deduce from this when we go back to the classical setting of forms over rings? So suppose that we have a ring R, and suppose that M is an invertible module with involution over R in the sense that we considered in the previous talk. In this case, there are several natural equivalences of Poincaré infinity categories. Each one gives its own fundamental theorem for rings. So the first equivalence is that if we take the perfect derived category of rings and we twice shift the homotopic quadratic Poincaré structure, then we get the homotopic quadratic Poincaré structure associated to the module with involution obtained by a sign twist from M. And this yields the following type of a Karoubi fundamental theorem that says that the homotopic quadratic V theory of Rm is equivalent to the loop on the homotopic quadratic U theory of R with M twisted by a sign. Similarly, if we look at the homotopy symmetric Poincaré structure and we shift it twice, then we get a Poincaré infinity category equivalent to what we get if we twist M by a sign. Now, I should warn here, these equivalences of Poincaré infinity categories are not given by the identity on the underlying stable infinity categories. If we fix the stable infinity category, these two quadratic functors are not the same quadratic functor, but there is an equivalence which on the underlying stable infinity category is given by suspension. And with that equivalence, these two quadratic functors coincide. And so here we get a version of Karoubi's fundamental theorem for the homotopy symmetric V theory and U theory. Now, what can we say for the genuine structures? So if we twice shift the genuine quadratic Poincaré structure, then we get a Poincaré infinity category which is equivalent to what we get if we sign twist the genuine even structure. And this gives us another fundamental theorem, which has another version of Karoubi's fundamental theorem, which identifies the genuine quadratic V theory with the loop of the genuine even U theory with M twisted. And finally, if we twice shift the genuine even, then we get a Poincaré infinity category equivalent to the genuine symmetric with the sign twist. And this gives us a version of Karoubi's fundamental theorem with the genuine even V theory and the loop of the genuine symmetric U theory with the sign twist. Now, when 2 is invertible in R, all these claims are equivalent to each other and are all equivalent to the classical Karoubi's fundamental theorem. However, when 2 is not invertible, when 2 is not invertible, the first two claims pertain to invariants which were not defined in the classical setting, the homotopy symmetric Grothendieck-Witt theory and the homotopy quadratic Grothendieck-Witt theory. For these two new invariants, we obtain that Karoubi's fundamental theorem holds as is. However, the second two versions of Karoubi's fundamental theorem pertain to invariants which actually do exist in the classical setting. So the genuine quadratic V theory is the V theory that one obtained from the classical quadratic Grothendieck-Witt theory defined using group completion. And similarly for the genuine even and the genuine symmetric, as we explained in the first talk, using the comparison theorem. And so these two versions of Karoubi's fundamental theorem give new statement on classical invariants. And in fact, they give a generalization of Karoubi's fundamental theorem to rings in which 2 is not invertible. And this precise generalization was in fact already predicted by Karoubi. Karoubi conjectured that this is what will be true when 2 is not invertible. And Giffen also predicted the same thing. So this is a proof of Karoubi's conjecture for how to generalize his fundamental theorem to the case when 2 is not invertible. Let us now collect some more consequences of additivity. In order to formulate them, we consider the following definition. So for a Poincaré infinity category, C copa, a full stable subcategory A inside of C is called isotropic if copa vanishes when restricted to A, and the inclusion of A in C admits a right adjoint. In this case, when we have an isotropic subcategory, then essentially by definition, A would be contained in its orthogonal complement, which is defined to be the collection of all objects Y such that the bilinear part associated to copa vanishes with Y with any X which belongs to A. And this would be true for any Y already in A by the condition that copa vanishes when restricted to A. So A would be contained in its orthogonal complement. And one can then show that if we take the quotient of A perpendicular mod A, so we take this quotient in stable infinity categories, this is called the Verdier quotient, then this quotient acquires a canonical Poincaré structure. And we call the resulting Poincaré infinity category the homology of A. And we say that A is a Lagrangian if its orthogonal complement coincides with A itself. That is, if its homology vanishes. So the homology measures how far an isotropic subcategory is from being a Lagrangian. And some examples of this are the following. So in the metabolic Poincaré infinity category associated to C copa, we have a Lagrangian consisting of the full subcategory of those errors which are equivalences. So this is a Lagrangian inside the metabolic infinity category. And inside Q1C copa, we have an isotropic subcategory, which is not a Lagrangian, but it is an isotropic subcategory, which consists of those spans which start from 0 and such that the second error is an equivalence. The homology of this isotropic subcategory is canonically equivalent to C copa itself. And similarly, in Qn C copa, there is an isotropic subcategory consists of those sequences of spans which start from 0, they go 0, 0, 0, 0, the 0 span, 0 span, 0 span, and the last span is of this form. So its second arrow is an equivalence. And the homology of this isotropic subcategory is Qn minus 1. And it is also natural in this context, since we have the notion of a metabolic Poincaré object is a Poincaré object which admits a Lagrangian. And similarly, when we have a Poincaré infinity category which admits a Lagrangian, then we say that it's a metabolic infinity category. And what this example says is that the Poincaré infinity category met C copa is in particular metabolic in this sense. And in the presence of an isotropic subcategory, we have the following theorem, which we call the isotropic decomposition theorem, which describes the value of a group-like additive functor on a Poincaré infinity category admitting an isotropic subcategory. And what the isotropic decomposition theorem says is that the value of f on C copa canonically decomposes as the value on the homology of A times the value on the hyperbolic Poincaré infinity category associated to A. And so now that we know that the GW space is additive, and we also know that it's group-like, we deduce that whenever we have a Poincaré infinity category with an isotropic subcategory, then the GW space of C copa canonically decomposes as a product of the GW space of the homology of A and the K-theory of A, which is the same as the GW space of the hyperbolic Poincaré infinity category of A. And if we use this last example and argue by induction, then we deduce that for any group-like additive functor, its value on the nth Q construction, Qn C copa, decomposes as a product of f C copa and n times the value of f on the hyperbolic Poincaré infinity category associated to C. And in particular, the Grothendieck-Witt space of Qn C copa decomposes as a product of GW C copa and n factors of K-theory space of C. And let us give one last example for application of additivity. I would like to show that the additivity that we proved for the GW space implies a classical Waldhausen's additivity for the K-theory space. So for this, consider a fiber sequence of stable infinity categories such that P admits a fully faithful right adjoint R. In this case, the hyperbolic Poincaré infinity category, hype D, admits a Lagrangian inclusion. So we have the functor from C times E op to D times D op. This is the underlying stable infinity category of hype D. And we have a fully faithful functor from C times E op to D times D op, whose first component is I. You're sending C to D by I, and R op and E op to D op via R op. And one can show that this is an isotropic subcategory that is in fact a Lagrangian. And from the isotropic decomposition theorem, one then deduces that if f from cat P to E is a group-like additive functor, then the value of f on hype D canonically decomposes as the value of f on hype C and the value of f on hype E. And if we now apply this in the example where f is the GW space, we deduce that the K-theory space of D canonically decomposes as K of C times K of E. And this statement is known as Waldhausen's additivity theorem. So the additivity theorem that we have for GW implies also classical additivity for K-theory. And I would like now to move forward towards the definition of the Grothendieck-Witt spectrum. So if you wish, we would like to deloop the Grothendieck-Witt space into a Grothendieck-Witt spectrum. And for this, we need to extend the perspective a bit. So we consider the notion of cobordism categories with coefficients. I would like now to define of cobordism categories. I would like now to extend this notion to cobordism categories with coefficients in an additive functor. So suppose that we have an additive functor f from cat P to spaces, and we have a Poincaré infinity category C copa. Then we can form the simplicial space obtained by taking the Q construction, applying it to C with a shifted copa, and then instead of taking the space of Poincaré objects, which is what we did before, apply the arbitrary functor f that we have here. And all we assume on this f is that it is additive. This assumption is enough to imply that this simplicial space is a Siegel space. We then define the f-based cobordism category, cob f C copa, to be the infinity category associated to this Siegel space. Now, if f is not just additive, but in fact, limit preserving, if it preserves all limits, then one can show that this Siegel space is also complete. However, for a general additive functor, this will generally not be a complete Siegel space. In the case where f is Pn, the functor that sends a Poincaré infinity category to its space of Poincaré objects, then this condition holds. This Siegel space is complete, and the resulting infinity category is the cobordism infinity category we had before. If f is both additive and group-like, then by isotropic decomposition, the space that we have at the nth place in this simplicial object decomposes as a product of fc copa shifted and n copies of f on the hyperbolic category. In this case, one can observe that this simplicial space is not just a Siegel space, but it is in fact a groupoid object in spaces, which is which is the action groupoid, which is also sometimes called the bar construction, associated to the translation action of the infinity group f applied to hype of C, acting on f of C copa shifted. So both these things are infinity groups. There is a map between these guys, which is induced by a natural Poincaré functor from hype C to C copa shifted. This Poincaré functor induces a map of infinity groups from this infinity group to this infinity group. Along this map, this infinity group can act by translation on the underlying space of this infinity group. And this simplicial object is nothing but the action groupoid of this action. And in this case, in the additive group-like case, this groupoid object is going to be complete if and only if f vanishes on the hyperbolic category. So usually not. And we can prove a generalized fibration theorem in the context of these cobordism categories with coefficients. And this generalized fibration theorem says that for every additive functor f from cat P to spaces, the functor that sends a Poincaré infinity category to the f-based cobordism category sends split Poincaré-Verdier projections to bicartesian fibrations of Siegel spaces. And a conclusion from this is that for every additive functor f from cat P to spaces, the functor that sends a Poincaré infinity category to the geometric realization of its f-based cobordism category is additive. This means that we can think of this procedure that takes f and gives us back the geometric realization of the f-based cobordism category. This is a procedure that takes one additive functor and gives us another additive functor. Since its source and target are the same type of object, we can now iterate this construction. For this to give us something useful, let us first observe the following. So there is the following commutative square. Here we have Q1 C copa shifted. So this is what appears at degree 1 in the simplicial object from which one will obtain the f-based cobordism category. And here we have the functor that is given by collecting the two face maps. So this functor sends a span to its source and target. And the fiber of this functor are those spans which go from 0 to 0. And this functor is clearly just equivalent to C itself. And if one checks what the quadratic functor of Q1 C copa shifted gives to such spans, it exactly gives the quadratic functor of C. And so we obtain an inclusion like this from C copa going inside the fiber. So in fact, we have here not just a commutative square, but in fact a Cartesian commutative square. And this induces a natural map. If once we apply f to this square, we will get a map from f C copa to the fiber of the map from f Q1 C copa shifted to f C copa shifted times f C copa shifted. In the Siegel object that encodes the f-based cobordism category, this fiber is exactly the mapping space from 0 to 0. And so this ends up giving a map, and the mapping space from 0 to 0 naturally maps to the loop space of the geometric realization. And so we end up with a natural map from f C copa to the loop of the geometric realization of the f-based cobordism category. And now we have the following lemma that says that if we start with a functor f that is not just additive, but also group-like, then the geometric realization of the f-based cobordism category, considered as a functor, is also group-like. And this map, considered as a natural transformation, is an equivalence of group-like functors. Let us indicate how the proof of this lemma. So first, since f is group-like, this simplicial object that encodes the f-based cobordism category is in fact a groupoid object, as we said. It is the action groupoid of the action of f of the hyperbolic Poincaré infinity category acting on f of C with copa shifted. The geometric realization of the action groupoid is then a model for the cofiber of the map from f of the hyperbolic Poincaré infinity category to f C copa shifted when this cofiber is computed not in spaces but in infinity groups. In particular, this cofiber is an infinity group. So this geometric realization is group-like. And since f is additive and group-like, we know from before that it gives the same values on the hyperbolic and metabolic constructions. And hence we can replace this cofiber with the cofiber of the map from f applied to the metabolic Poincaré infinity category of C copa shifted to f applied to C copa shifted. And so if we want to show that f identifies with loop of the cofiber, then if one unwinds what map we used to check what map we want to show is an equivalence, one sees that in fact what one needs to show is that this sequence, which is obtained by applying f to the metabolic sequence, is a fiber sequence. So this would identify f with the fiber of this map and consequently with the loop of the cofiber. And one can check that this is the same identification that we were after here. And so this is just a consequence of F being additive, since F being additive, since the metabolic sequence of C-copper shifted is a split Poincaré-Verdier sequence. So let us summarize what we have so far. So we have shown that if F is additive and group-like, then if we take the F-based cobordism category, take its geometric realization, and apply loop space, then the result is naturally equivalent to F itself. And so in particular, this gives us a delooping of F in the form of the geometric realization of the F-based cobordism category. And so we can iterate this delooping in order to form an omega spectrum. So given an F that is additive and group-like, we define the spectral F-based cobordism to be the spectrum-valued functor from cat P to spectra, which sends a Poincaré infinity category C-copper to the spectrum object, to the omega spectrum object, consisting of the sequence of spaces F0 C-copper, F1 C-copper, etc., where F0 is F, and Fn C-copper is defined as the geometric realization of the Fn-1 based cobordism category. The structure maps are given by the equivalence between Fn to loop of Fn plus 1 issued from this natural equivalence. And so for any group-like additive functor F, we obtain an additive functor to spectra whose infinite loop space is F itself. We hence obtain an omega spectral delooping, or an infinite delooping of F in the form of a spectrum-valued additive functor. And so the conclusion is that any group-like additive functor has a distinguished additive delooping. Though one should note that this is not the unique additive delooping. It is just distinguished. It is in fact the initial additive delooping. And we define then, this leads us to the definition of the Grothendieck-Witt spectrum, which we define by applying the procedure that we had just constructed to the space-valued group-like additive functor GW space. And so we define the GW spectrum to be the spectral construction, cobordism construction, applied to the GW space. And if one unwinds the definition, the individual spaces that sit in this omega spectrum GW are usually referred to as the iterated Q construction. So there will be, the first term involves just geometric realization of Q construction. The second term will involve geometric realization of a twofold simplicial space involved iterated application of the Q construction, etc. So this can also be considered the definition of Grothendieck-Witt spectrum via iterated Q construction. And so to summarize some of the key points, GW is an additive functor from cat P to spectra. It is a Hermitian analog of the algebraic theory spectrum. This spectrum is a connective spectrum whose infinite loop space is the K-theory space. By contrast, the GW spectrum is generally not connective. So if we go back for a moment here, any additive functor has a distinguished delooping, but this delooping is not connective in general. And Stichting also defined the Grothendieck-Witt spectrum in the setting of linear DG categories in which 2 is invertible. So Z half-linear DG categories. And our construction agrees with his in this context. Stichting also defined a different type of a Grothendieck-Witt spectrum in the setting of exact categories. That construction is not the same as this GW, but instead we believe that it is equivalent to a localizing variant of GW, which we call the Karoubi Grothendieck-Witt spectrum, and which can be defined in the setting of Poincaré infinity categories. Finally, an example, if we take the hyperbolic Poincaré infinity category associated to a stable infinity category C, then its Grothendieck-Witt spectrum is canonically equivalent to the K-theory spectrum of C. And if we apply additivity in the case of the metabolic sequence, then we obtain the spectral version of the Bode-Genau sequence, which says that the forgetful and hyperbolic map on the level of GW and K-theory spectra fit into a fiber sequence of spectra. And since K-theory spectrum is connective, we obtain that for every negative index I, the boundary map associated to this fiber sequence gives an isomorphism between the ith homotopy group of GW, which we write here as GW subscript I, or the ith GW group of C Copa, and the boundary map gives an isomorphism with the I-1 GW group of C with Copa shifted, so what appears here. And if we now argue by induction, then we see that for a negative n, if we look at the nth GW group of C Copa, so by definition the nth homotopy group of the GW spectrum, then applying this once shows that this is isomorphic to the n-1 Grothendieck-Witt group of C with Q shifted in the other direction. And then we iterate these isomorphisms, we arrive all the way to GW-1 of C Copa shifted n-1 times. And now applying once more the boundary map from this fiber sequence, in this case all the way up, identifies this with the co-kernel of the map from K0C to GW of C Copa shifted n times. And this is the same, as we saw in the previous talk, as the zeroth L group of C Copa shifted n times, which in turn is the same as the nth L group of C Copa. And so the conclusion is that the negative homotopy groups of the GW spectrum are the same as the negative L groups. And we now come to the last topic that I would like to talk about, and that is the universality of Grothendieck-Witt theory. So we proved two universality statements. The first is universality for the GW space, and that is the statement that the natural transformation from Pn to GW exhibits GW as the initial group-like additive functor to spaces under Pn. The second theorem is a universality statement for the GW spectrum, which says that the natural transformation from the suspension spectrum of Pn to the GW spectrum exhibits the GW spectrum as the initial additive functor to spectra under the suspension spectrum of Pn. And so we can consider the GW space as simply obtained from the raw invariant that sends a Poincaré infinity category to its space of Poincaré object by forcing the condition of being group-like and additive. So it was already additive, and now we force it to be group-like and additive. And similarly, the GW spectrum is the universal thing that we can obtain from the raw invariant Pn if we want a spectrum-valued invariant that is additive. And both these theorems can be deduced from the following key statement, which in principle simply says that the Q construction realizes the suspension in additive functors. So more precisely, the operation that sends F to the geometric realization of the F-based cobordism category, which can also be identified with the geometric realization of the simplicial space obtained by applying F to the Q construction, realizes the suspension in the infinity category of additive functors from cat P to spaces. And this means that we can identify the GW space as the loop suspension of Pn, and the map from Pn to GW is a canonical map from any object to the loop of its suspension. And in this case, we already know from before, from the lemma that we proved before, that on group-like objects, on group-like additive functors, so group-like objects here, the map from the group-like object to the loop of its suspension is an equivalence. This means that in the context of this infinity category, suspension is in fact fully faithful when restricted to group-like objects. And in this case, one can show from completely formal considerations, which have nothing to do with specifically GW or the Q construction, that that in in this context, the map to loop of the suspension always realizes the group completion, or the universal group-like object under a given object. And this also somehow relates us back to the classical definition of the GW space, which was defined in the case of rings and projective modules over rings with unimodular forms by an actual process of group completion. So here we get, again, a sort of a group completion, but it's not a level-wise group completion. It's not that for every specific C copa, the GW space of C copa is the group completion of Pn C copa. Instead, GW as an additive functor is the group completion of Pn in the infinity category of additive functors. And similarly, what we can also deduce from this QE suspension theorem is that the GW spectrum is nothing but the suspension spectrum of the GW space. More generally, this spectral valued cobordism construction that we did before, this distinguished delooping that we had for group-like additive functors, is nothing but their suspension spectrum when we think of spectrum objects in group-like functors. Let us now indicate briefly how we prove this key statement. So we would like to prove that the operation that sends an additive functor in spaces to the geometric realization of the F-based cobordism category is nothing but the suspension. And we do this as follows. So we define Poincaré infinity categories null and C copa as the fibre of the Poincaré functor from Qn plus 1 C copa to Q0 C copa. This is one of the structure maps in the simplicial object that we have. It's the simplicial operator that is associated to the map in delta from 0 to n, whose image is 0. This gives us a Poincaré functor from Qn plus 1 to Q0. Q0 is just C copa. And we define null and C copa as the fibre of this. Now, this functor, if we identify objects in Qn plus 1 as encoding composable sequences of n plus 1 spans, so this is the underlying stable infinity category, encodes composable sequences of n minus 1 spans. This functor just sends such a composable sequence to the domain. So the fibre are those composable sequences of n plus 1 spans which start from 0. And this is invariant under the duality. It becomes a Poincaré infinity category. And the Poincaré objects in this Poincaré infinity category simply correspond to n plus 1 sequences of cobordisms starting from 0. And this can be organized into a simplicial object in Poincaré infinity categories by letting this n vary. And this simplicial object in Poincaré infinity categories fits into a fibre square of simplicial objects, where here we have the constant simplicial object on C copa. And here at level n, we have the functor from null n C copa shifted to Qn C copa shifted, which is induced by the boundary map from n plus 1 to n, which is the boundary map that is opposite to 0. So this boundary map sends a sequence of n plus 1 composable spans to simply the last n spans. Here we restrict to sequences of n plus 1 composable spans starting from 0. And this thing just remembers the last n composable spans. On Poincaré object, it will be the last n composable cobordisms. And the fibre at each level can be identified with C copa. So this gives us a fibre square in simplicial objects in Poincaré infinity categories. And if we apply f to this simplicial object in Poincaré infinity categories, so what we get here is just f applied to the Q construction with Poincaré structure shifted. So before we take a geometric realization, this is the simplicial object that encodes the f-based cobordism category. If we look what happens at n, what happens at null n, then before taking geometric realization, this simplicial object in spaces encodes a related infinity category. You take the F-based cobordism category and you slice it under 0. So it encodes the infinity category of objects in the F-based cobordism category equipped with the morphism from 0. And now if we apply geometric realization, then this becomes the geometric realization of the F-based cobordism category. So this is what we want to prove is the suspension of F. Here we get the geometric realization of an infinity category which has an initial object, which is the identity from 0 to 0. And hence this geometric realization is contractible. Here we have F, here we just have a point. And so we can reformulate our goal by proving that this square, when interpreted in the infinity category of additive functors, is co-Cartesian. So here F lives in this infinity category, it's an additive functor, and we already know that this construction gives an additive functor, so this also lives here, and this is just equivalent to the trivial functor that gives the point to everything. It's also additive and also lives here. And want to show that this square is co-Cartesian in this infinity category. And the idea is to show that the operation that takes a functor and precomposes it with the nth Q construction has a right adjoint, which is obtained by precomposing F with a dual Q construction, which is itself left adjoint to the Q construction. So precomposing with the left adjoint gives a right adjoint on the level of functors. And what is this dual Q construction? So I will not give the general definition, but let me just give, so for example, in the case of n equal 1, the dual Q construction in degree 1 is the Poincaré infinity category, whose objects are cospans. So these are diagrams like this, where we have x, x prime, and maps to W. And the Hermitian structure sends a cospan like this to the push-out of spectra of coppa x prime, and coppa W. Compare this with the usual degree 1 Q construction, whose objects are spans instead of cospans. The arrows here go the other way. And the Hermitian structure sends a span not to the push-out, but to the fibre product of the corresponding spectra. And similarly, the dual Q construction in degree n would be an infinity category whose objects are certain diagrams which encode sequences of n-composable cospans. And the Hermitian structure is going to be given by applying coppa to this diagram and then taking the co-limit in a dual manner to what happens in the degree n Q construction, where we have spans and the Hermitian structure is obtained by applying coppa and then taking the limit. And there will also be a dual to null n C coppa. It would be a Poincaré infinity category which sits in a split Poincaré-Verdier sequence like this. So it is in fact the co-fiber in cat P of a Poincaré functor from the dual 0 Q construction to the dual n plus 1 Q construction, whereas the original null was the fiber of the map the dual map from the usual Q construction in degree n minus n plus 1 to the Q construction in degree 0. And so now we can argue by adjunction. So basically, in order to show that we have this square in additive functors, and we want to show that it's co-Cartesian, and or that it's a push-out square. How to show that something is a push-out square? Well, we can choose a test object G, something that lives here, and map this guy into it, and show that this gives us a pullback square of spaces. Now, to all these things, there are adjunctions. So these are geometric realizations. They are colimits. Mapping out of a colimit becomes a limit. Then the operation of precomposing with null has a right adjoint, which is precomposing with null dual. The operation of precomposing with Q has a right adjoint, which is precomposing with Q dual. The operation of shifting also has a right adjoint, which is the inverse shifting. And so we obtain that in order to prove that the original square is a push-out square in additive functors, it will suffice to show instead a dual statement that for every test object G, so G needs to be an additive functor to spaces. So for any G living in additive functors, this square that we obtain by dualizing all the construction is a fiber square of additive functors. And since totalization preserves pullback fiber squares, we can check this level-wise. In fact, we can also check this level-wise, and we can also check this level-wise for every at every Poincaré infinity category separately, because this is just a question about limits of additive functors. These are like limits in functors. And so it will just suffice to show that for every Poincaré infinity category, C copa, what we get here in degree n when evaluated at C copa is a fiber square of spaces. So what we get at degree n of these simplicial objects and at C copa is exactly this sequence. So we need to show that this is a fiber sequence of spaces. And this sequence of spaces is obtained by applying G to a certain sequence of Poincaré infinity categories. So the sequence that goes from the dual Qn, C copa, dually shifted, to the dual null of C copa dually shifted to C copa. And so in order to show that since G is some additive functor to spaces, in order to show that this is a fiber sequence of spaces, it will suffice to show that this is a split Poincaré-Verdier sequence. Now, at this point, one can apply to general principles and somehow show that it will be enough to check the dual sequence, which is more familiar, which involves the dual Q construction and the dual null construction, in which case these things are more familiar and easy to check. But even without applying to these general principles, these dual guys can also be sufficiently unwind so that they are all these Poincaré infinity categories become very explicit. These functors become very explicit, and one can also just verify by hand that this is a split Poincaré-Verdier sequence. So this is the end of the proof, and hence also the end of the proof of the universal properties for the GW spaces and the GW spectra. So let me finish here the second talk. In the third talk, I will start talking about the relation between the GW spectrum and the L theory spectrum. I will then prove the fundamental fiber sequence relating GW spectrum, the L spectrum, and the algebraic theory spectrum. And given that in Marcus's lecture, Marcus would have already proven many, many things about L groups, I will be able to consequently deduce many, many things about Grothendieck-Witt groups. So see you all next time, and thank you for listening.